There are two primary applications in the exponential chapter, and the first being compound interest. So the compound interest you see here talks about when you are compounding money either annually, semi-annually, quarterly, monthly, but you will see the word compounded followed by one of those descriptors in the story problem. So that will be how you will know you use this formula. A will be the ending amount, P will be your principal or your starting amount, R is going to be the interest rate entered as a decimal, so 5% would be entered as 0.05. Then it is divided by n, and there's also an n up in the exponent, and that stands for the number of times it is compounded in a year. So that would be the descriptor. So compounded annually would be once a year, compounded semi-annually twice a year, and so on and so forth. And then the T stands for the number of years. So example A is talking about Jim who would like to buy a new car in 3 years. He has $2,000 saved in a bank, and that earns 4.5% interest compounded quarterly. If he does not add or withdraw any money, how much will be there in 3 years? So reading that through, 2,000 will be my starting amount. That'll be our P value. 4.5 will be our interest rate. So anything with your percent will be your interest rate. Quarterly will be our N value, how many times it's compounded in a year. So that will be 4 times. And then 3 will be our T value. So our equation will look like this. And then once you have that set up, you will be able to type that in your graphing calculators exactly as written, and you should get $2,287.35. Things to point out, again, the 4.5% was entered as 0.045. And then the n is in the bottom of this fraction, and also again in the exponent, so you use the value 4 for quarterly twice. Example B is talking about Lucy, and she's investing $6,000 in a CD, paying 5% compounded semi-annually. Again, there's the word compounded, so we know to use this formula. How much did she have 4 years ago? So this one is a little bit different where we're talking about time previous to where we are at. So that's going to change our T value. Our 6,000 again will be our our starting value, our P. Our interest of 5% will be 0.05. Semi-annually would be twice a year, so I'm going to enter that for n down in the bottom of the fraction and also in the exponent. And now 4 years ago means I'm going to enter -4 for my time. So if I'm thinking about this logically, if I have $6,000 now and I'm going back in time, my value should be less than 6,000. And indeed it is, $4,924.48. So anytime you're going previous in time, you just want to make that exponent negative. Example C is talking about a bank giving a certificate paying an interest rate of 4.3% compounded semi-annually. This time the value is in there for 2 years and 6 months. So I'm going to use the same setup where 500 will be my P value. I'm going to turn the 4.3 into 0.043. Semi-annually twice a year will be the value below the fraction and in the exponent. But my time I have to turn to years. So 2 years and 6 months is 2.5 years. So make sure that you are thinking about the number of years always to plug in for your T. So if you plug that in accurately, you'll get $556.11. Question D and E are talking about effective annual yield, and what you are looking for here is a percent. So what you're going to do is you're going to think about how much money you would make on $1 for 1 year. So I'm always going to plug in $1 for the P and 1 year for the T, and then I will use the 7% as 0.07 and quarterly for the 4. So that will be my 2 N values. So when I plug that in, I will get 1.07186. Well, to figure out the percent that I make, I can't include the $1 because that's what I invested. So I take away the $1, meaning in that 1 year, my $1 made 0.07186. So since we use $1, that also translates to 7.186%. So your effective annual yield, you will always turn into a percent for your final answer, and you are looking at $1 for 1 year. So let's try another one of those. Question E is looking at the effective annual yield for 3.8% compounded monthly. So again, I'm looking at how much I would make on $1 for 1 year. The 3.8 turns to 0.038. Monthly is 12, so I'm going to use that for my N value. And when I get that value, that means I have $1.03867. Well, I already had $1, so I have to take that away. So that leaves me with 0.03867. and that would also then turn to 3.867%. So that is your first application, compound interest. Our second application is on geometric sequences. We have studied arithmetic sequences and now we're looking at geometric. So things today will look very similar. The difference is arithmetic had a constant difference, meaning you were adding a value every time. Geometric means we're going to have a constant ratio, which means we're multiplying by the same value each time. So our explicit formula is listed here. G sub 1 is your first term, and then you're multiplying by the ratio r, and then to the n minus 1, so that looks very similar to arithmetic. Recursive, again, looks very similar. G sub 1 is your first term, r is your ratio, and then g sub n minus 1, just like before, means your previous term. You're just multiplying that ratio in the previous term, where if you looked back to your arithmetic notes, there would have been a plus d in there instead of an r times. And again, we still have the n greater than or equal to 2 on the recursive formula. To help you find the ratio, if it is not obvious, you are going to take the second term and divide it by the first term. So let's try a few of these. Find the first 4 terms in the sequence -1 times the quantity 3 to the n minus 1. So -1 is the first thing listed, that's my first term, and my ratio is 3, meaning that my first term is -1, I'm going to multiply by 3. So that would give me the sequence -1, -3, -9, -27. In the recursive formula over on the right, my first term is 3, and then the 5 stands for my ratio because that's what I'm multiplying the previous term by. So first term of 3 multiplied by 5 gives me the sequence 3, 15, 75, and 375. Working the other direction, finding the formula for the sequence 6, -1.2, 0.24, -0.048. To me, that's not as obvious what that ratio is when I'm multiplying by each time. So in order to figure that out, I'm going to take the second term, -1.2, and divide it by 6, and that will give me my ratio of -0.2. So now I know my first term is 6, my ratio is -0.2, so I can plug those values into my sequence. G sub n equals 6 times the quantity -0.2 to the n minus 1. Part C, the sequence 0.5, 5.5, 60.5, 666.5 looks like a ratio of 11. I'm multiplying by 11 each time. Again, if that wasn't obvious to you or you couldn't figure that out, you would take 5.5 and divide it by 0.5, and that would give you a ratio of 11. So my first term is 0.5, and then I would plug in G sub n equals 11 times that previous term, so G sub n minus 1, and then n greater than or equal to 2. So very similar to before, the terminology and the notation should look very similar. You are now, though, instead just looking for what you're multiplying by, not adding. Example D, find the first 5 terms for the geometric sequence with a first term of 6 and a second term of 4. So I know my first term, but I also need my ratio. So to find my ratio, I'm again going to take that second term and divide it by my first term. So 4 divided by 6 gives me a ratio of 2/3. So I know my first term is 6 and my second term is 4. To find my third, I'm just going to multiply by 2/3 and then multiply that by 2/3, etc. So that will leave me with the sequence 6, 4, 8/3, 16/9, and 32/27. So just multiplying by that ratio each time. Example E wants to know, is this sequence geometric? So geometric meaning we're multiplying by the same value every time. So 3, 6, 9, 12, 15 is adding 3 each time. Adding 3 each time makes something arithmetic, meaning this answer is no, it is not geometric, because to be geometric we would have to have a constant multiple or a constant ratio, not a constant difference. And our last 2 examples are applications. So suppose a ball is dropped from a height of 5 meters and bounces up to 90% of its previous height. Write an explicit formula. So be very careful here about what a first term would be versus a 0th term. Suppose it drops from a height of 5 meters, meaning at time 0, the height is 5. So to find my first term after 1 bounce, I would have to do 5 times 90% to get a height of 4.5 after my first bounce. So my first bounce would be 4.5, and then 90% would be my ratio. So my then formula would say G sub n equals 4.5 times 0.9 to the n minus 1. So just be very, very careful there. But then once I have the formula, how high will it be after its 10th bounce? Then I can just plug in 10 for n and then find out that it would be 1.74 meters high. So similar, in example G, a car sold for $22,000 new, but its value decreased 12% each year. What is the value after 5 years? So again, I need my first term and my ratio. My first term is not 22,000. After the first year, it would be 88% of that. So where did I come up with 88%? If it goes down 12%, that means that it's still worth 88%. So I took 12 away from 100 and then turned that to a decimal. So to find my first term, I'm going to do 22,000 times 0.88. So after 1 year, the car is worth $19,360. So now I can use that in my ratio to find my formula. G sub n equals 19,360 times the quantity 0.88 to the n minus 1. And then to answer the question, after 5 years, I'll plug in 5 for n, and then my car will be worth $11,610.10. So those are your two applications in the exponential chapter. Bring questions to class tomorrow.